All right, good afternoon, everyone. Let's get back to our neural network discussion. So the main thing we were talking about last time is the details of how we compute the gradient, which is a lot more complicated in this case because we have many stages of nonlinear processing going on. So again, our objective is to do this mini batch stochastic gradient descent. Our new parameters equal our old parameters minus small positive step size times the gradient of the loss. Here we're writing that gradient as a sum of pieces of data that could be images over the batch, and the batch is going to change. So every update step t, we have a new mini batch. So that's what the IT is. Even the size of that could possibly change. And our overall loss, we write like this, and it's the sum of these losses on the individual samples in our mini batch. Okay, so how do we compute the gradient? So in particular, the network parameters for us now are the weights and intercept terms for the hidden layer, and then the weights and intercept terms for the output layer. So in general, these W's are matrices and the B's are vectors. So we have all these different gradient quantities to compute. And the way that we do that in an organized fashion, that allows us to really handle any kind of architecture for a network, is we build its computation graph. So that is a graph that shows the dependencies of the different variables on each other. So here we have our parameters in blue. We have our data in green. This is over a single batch. And then we have the final loss here, and then all the intermediate quantities we need to compute to get us to that loss. So the way that we process the data to compute the loss and the gradient is first we go from left to right, and we compute each one of these things in turn. Finally, we get our loss, and then we go from right to left. That's the backward pass, and we compute the gradients through a procedure that we were discussing. So we'll get back to that discussion today, but then just to summarize the forward pass for this two-layer network, these are the equations. So for all the elements in our batch, we need to compute these hidden scores. So this is the hidden score for the ith element of the batch. Then we put the hidden scores through this nonlinearity, which operates element-wise on these to get our hidden activations. Then those hidden activations go through our output linear layer to get us our output scores. And finally, we're constructing our cost based on our output score, our training label, and we sum across the batch to get our final cost for that batch. Okay, so then to prepare for understanding the backward pass, we reviewed the chain rule. So if I have a computation graph like this, and I want to do dz dx, I can do that by the chain rule as dz dy times dy dx. Now if we insert another variable here, we can use that if we want, or we can ignore it and we can sort of skip over it. We can do dz dy dy dx equals dx dz. And that's useful because we have a pretty long graph here, so that means that if I'm working on this, I could skip an intermediate node. And then the final thing, which we'll talk more about today, is the multivariate chain rule. It basically says that whenever you have a node that really is sort of like a collection of nodes, you have to think about how the data flows through that node. And like in this case, if the dependency structure is that information about X goes through these different yi nodes to get to U, then if you do something like dz dx, you actually have to consider all the different ways the information flows. So you have dz dy1, dy1 dx plus dz, dy2, dy2 dx, and so on. And so finally, you get this summation over these intermediate nodes there. Okay, so any questions on anything so far? Okay, great. So then we were putting this together, and we were going through this exercise of understanding how we compute these gradient terms, and we're starting, in this case, in the simplest case, where we have a batch size of 1, and we have scalar variables. That means that all these nodes just have one scalar associated with them. And so here is the forward pass. We would go through, so at the start of the iteration, we know our data, we know our parameters that we've learned in the previous iteration, and so we go through and we compute the purple nodes by going through those steps. At the end of that process, we have values for all these things computed, and now we can work backwards to get the gradients that we need. So working backwards, we would start by computing dj, dzo, and to do that, we look at this step of the dependencies, and we notice that, okay, we have some cost j. The specific incarnation of that cost depends on whether we're doing regression or classification or what. And so right now, we just know enough to say that we can differentiate it. I'll show you some examples of that later today, of what specifically this is. Okay, then once that's computed, we can do dj dah by doing dj dzo times dzo dah, like this. So that's the chain rule. And conveniently, we already computed the first term, so that's just a number we plug in. And for the second term, in this case, looking at this dependency structure, we see that dzo dah is just wo. And so now we know that's just a value that we know here. And so now we have computed this. Now we can move on to dj dzh. We do that by dj dah times dah dzh, like this. Conveniently, we already computed the first term, so we plug that in, and then we just have to do dah dzh. You can see what that is here. It's going to depend on the exact choice of activation. We'll be general for now, and we'll just say whatever that is. Let's say we can differentiate it, and so we'll just write this as h prime evaluated at zh. So now we have everything computed in preparation to do the gradient with respect to our parameters. So the first one be dj dbo. So here we do dj dzo times dzo dbo. And conveniently, we've already computed that first thing, so we just plug in that number. And now for dzo dbo, we can look at this equation, and we see that's just going to be 1. Okay, so now we know dj dbo, and that will be used in our gradient descent in order to update the parameter of value for bo. We can also do dj dwo, and that is going to be dj dzo times dzo dwo. Again, we already computed dj dzo, so we can reuse that. And now we just have to worry about dzo dwo. And from this equation, we can see that that's just going to be ah, and ah is something that we already computed before, so we can just plug that in. And so on. And so in this way, you can also do dj dbh as dj dzh dzh dbh. And we get similar equations as before. After we've done all this, we now know all of our gradient terms. We're ready to do our gradient, stochastic gradient descent update. And then we move on to the next iteration. Now we have new values. We begin the forward process, or the forward pass, and then once we're done with that, we do the backward pass. Okay, so that's the overall procedure stated in its simplest form, with scalar variables and batch size b equals 1. All right, so before we get on to slightly more complicated notation, any questions on this? Is this making sense, the overall kind of procedure? Yeah. Does it seem complicated or not so bad? Not so bad. Okay, at least some people say not so bad. Good. Okay, so now let's keep all the variables scalar, but let's increase the batch size to greater than 1. So in that case, like we have several scalar features in our batch, and then each one of those scalar features, according to this equation, would then affect a corresponding scalar score ZH. So the point here is when you think about, okay, so there's definitely several xi's here, several zh's here, and so on. But if you think carefully, they're decoupled in a certain sense. So maybe this is I equals 1, I equals 2, and you can see that, so like x1 affects zh1, but x1 does not affect zh2 because of the way this works, right? It says that everything is decoupled across i's. Same thing happens in going from the hidden scores to the activations. Same thing again happens from the hidden activations to the output scores, but then everything does get combined using this sum in that last node. Okay, so that's really the difference here. So essentially we have several of these, but they're all working in parallel. So I'm going to try to make this look pretty, but those are sort of our nodes. Okay, so essentially forward pass is very similar to before. It's just that we do these steps several times for each element in the batch. Then when we're all done, we sum across the batch to get our final loss for that batch. Now, working backwards, here I'm going to write all the gradients just in terms of scalars. So just to keep everything simple, I'm not going to vectorize anything yet. So here we're looking at, for example, dj dzoi for some I. So maybe like you could say I equals 1. That's just essentially the same equation we saw on the previous slide, right? Nothing different. And then we have, again, let's just pretend I equals 1 for sake of discussion. If I want to do dj dah1, then that's just dj dzo1 times dzo1 dah1, right? So that's, again, same exact equation as last time. And so on. So everything here, when we do these gradients, it's just exactly the same as a previous slide, except we have an I dependence. Okay, everybody with me on that? Okay, so now let's think about the parameters. Here gets a little trickier. So if I want to do dj dbo, maybe to draw a slightly more complete diagram here, this BO is actually going to affect all the items in the batch, right? So this BO affects this one and this one and this one, and then so essentially there's like, you could see there's several parallel paths between BO and J. So this is a case where we have to apply the multivariable chain rule. And so that would be this equation dj dbo. We have to sum over those different i's of dj dzoi times dzoi dbo. The actual individual elements, those are very similar to the previous page. So these things we already computed, dzoi dbo, we can get that by looking at this equation, just doing that derivative and seeing that it's 1 no matter what I is. Okay. And then we do similar dj dbo. Again, we have the same paths, b different paths for a batch size of b. And so we get this equation, same as the previous page otherwise. And something similar happens for the hidden weights. So we have, again, to draw the more complete picture, we have several So BH affects all the elements in the batch, and then each of those eventually goes to the cost here. So you have, again, several parallel paths. We have to use the multivariate chain rule. And so we see the same summations over I for dj dBH as well as dj dWH. Other than that, all the other equations are the same. Okay, so is everybody still with me so far? Okay. Yes.
For the gradients of the parameters, do we have to like normalize it, or so like we can use it for gradient descent?
Do we have to normalize it? No, we don't want to do any normalization. Yeah, I'm not sure what you had in mind with the normalization.
Because it's like it's summarized over all the i's.
Mm-hmm.
So it's would it be like too big to apply to the
I mean, I think, maybe you're asking about the fact that, let's see. Is it that somehow I dropped this part? So maybe, okay, because here we were normalizing by the size of the batch. This is sort of, it was more for almost a notational. The reason I did that is that was sort of key in convincing you that this gradient approximation is correct on average. So that's really why I put that in there. Whether you actually do that in practice or not, I don't think it affects things too much. But then, yeah, so the normalization, I guess the way I'm handling it here is if we're going to use it, then it comes into the stochastic gradient descent update, whereas right now we are just looking at the gradients of this with respect to the parameters. So, okay, so that's, yeah. Normalization is not really super important right now. Okay, any other questions about anything here? Okay, great. So let's now move on to the case of vector variables and a batch size of b greater than 1. So here what's complicated is that there are sort of two dimensions of multiplicity. So when you look at a node like this, you can see that on one hand, there's several different i's in the batch. But on the other hand, even for a given I, you have multiple ZOs, right? That's a vector that has possibly many entries in it. So in some sense, if you want to collect these quantities across I, you actually could write it as a matrix. So you have two different degrees of freedom here. So the way that I'm doing the notation here, you can see that the ZOs, I'm using I and K. So K, if you want to just write a little variable, K will be the variable that we use as we index down across the elements of the Z vector, and then I is still the elements across the batch. Okay, so keeping the calculus only scalar, because I think scalar calculus is a lot easier than vector calculus, at least until you're an expert. So here we're looking at something like dj dZO, but we're looking specifically at the ith batch element and the kth entry in this vector. So for that, we just look at this equation here, and so because I'm looking at a specific I here, all the other i's that are not this I, they fall away. But then I still have to look at the dependence of this on one particular entry within this vector. So that will be this. So I'm just looking at the partial derivative with respect to the ith batch element and kth entry. Okay, so that's the first one. And what about the next one? So here, again, on one hand, there is some decoupling across I that we saw before, right, where this is across I. But if I fix I, there is actually some coupling across the elements here. So let's look at that. Okay, so first of all, we have DJ DAHIL. So we're looking at ith entry, and in this case, we're using L to index down that vector. And so when we look at, so roughly speaking, we have DJ DZO, DZO DAH, but now we have to be a bit more careful. Okay, do we need a sum across I? No, because when we looked across I, there was a decoupling. So we can use the same I here, and here we don't have to do any sum across I. However, when you look at these equations like here, and you ask how, you could say like, how does the elf entry here, how does it flow all the way to this cost, J? Okay, so the elf entry here will multiply the elf column in this matrix, right? And when it does that, it affects all the elements in ZO, not just a single one. So even if I just look at changing, minutely changing one of these elements in here, it affects all of these ZOs there. So essentially, when you think about it, for a fixed I, there's a bunch of nodes here, and a single elf element goes through all of them. So now we need to do a sum over all the elements in Z, which we're using the K variable for. So that's why we have a K here. And in particular, so we have DJ DZO IK, and then what is DZO IK DAHIL? So here we have to sort of visualize this matrix. We're looking at the elf column, and since we're looking at the kth entry of ZO, that means we must be looking at the kth row. So that's the dependence of one element in this Z from one element here. You're looking at a particular row column combination. In this case, it's just WOKL. So that's this part. So that's sort of the hardest thing on this slide. That's the main difference from the previous slide. Are there any questions on this? Yes.
What did you say about decoupling? We don't sum over I. What was that part again?
So yeah, so on one level we have, maybe I'll draw them again, like we have some nodes that change over I, right? Oops. Okay, so we do have some, didn't want to draw that. We have a multiplicity of variables in this because we have different batch elements. But each of those batch elements has an entire vector. So when we look at a particular I, let's say I1, and let's say that's this one versus the other ones, we still have to, say how does a particular element within the A vector in this node, how does it affect J? Well, it goes through all these elements in ZO1. And that can be seen from this equation. So a particular element in this vector will multiply this entire column and therefore affects all of these ZOs. So, yeah, so from another perspective, there's a decoupling across I, but there is a coupling across the other index, which we're calling K. K is what's indexing within the vector Z. So that's why we have this multivariate chain rule summing over K. Okay, so that's the trickiest thing on this page. Is this making sense, or can I answer any questions about it, or describe it further if needed? Okay, so it's important that you're able to, given a problem, understand where you need to put these summations in. It really just depends on the dependencies in these equations. Which things are decoupled, which things are coupled. That's what you have to be able to recognize in order to write these equations properly. Okay, any questions on this part? All right, no questions? Okay. All right, and then now, this next part, the relations here, even when you think about a vector here, there is a decoupling across the elements in the vector when you go between these nodes, because we said that this nonlinearity, this activation function, this guy operates element-wise. So the first element of this vector is only dependent on the first element in this vector. The second one here is only dependent on the second one here, and so on. So here there really is a decoupling in both domains. So that's why there's no summation over k in this equation, because there's decoupling both across I and across the other variable, which we're calling L. All right, so is this stuff making sense, or is it starting to get really complicated? Complicated, okay. Is there any specific questions I could answer about it? Don't be shy. If someone has a question, probably other people have the same question. Okay, yeah.
So could we also think of the sum of k as arising from like writing the matrix vector multiplication of W0 with AH
As a sum.
As a sum.
Exactly, yes. Right. If you just write the equation for let's say the kth element here in terms of all of these, you'd have a sum over I guess in that case you'd have a sum over L. So what do we want to do here? We want to write, I guess we're doing something slightly different. We're writing trying to think how can we think about it that way. Maybe the answer is no, because when I think about writing this as a sum, it would be a sum across the columns of here or down here, and that's not what we want to do right now. The sum is actually over the other direction. So I like to think about it as just how many paths can you make between, let's say, the L variable here and j. You end up going through all of the different elements of the ZOI, and therefore that's the variable you need to sum across in the chain rule. Okay, good. Question? Anything else? Yeah.
So is there anything about decoupled and coupled is like the branches being independent versus like all as one group?
Yeah, sort of like processing paths, whether they're independent or whether they're mixing somehow. So, like, I don't know. I guess I think about it like how many different ways can you go from here to here for a specific element in here? How many different paths can you go? How many paths does that information flow through to get to J? And it flows through all the elements of this vector, so that's where the sum is coming from.
So when we go from AH to J, we pass through ZO, and then we need to sum through all the elements of K's of the ZOs to get to J.
Yes.
So then how come when we go from ZH to J, we don't need to have like a sum in the AHs and the ZOs again?
So when you think about from here to here, you have this equation. And because this activation is applied independently to every one of those scores, there's no coupling across the vector elements going from here to here.
So there's no sum because it's based off of that equation that relates them?
Yeah.
Okay.
Mhm.
And then those are like given, that's not, or is that like a general form for all the nodes?
Well, for the way that we constructed this particular network, this is the architecture. If we would have constructed our networks in a different way, there might have been, different equations describing the forward pass. The computation graph itself could have had a different structure. So, but like for any kind of sequence of processing steps, you could draw a computation graph which shows you how all the variables are connected to each other. And then you sort of go one way with the forward pass and then back the other way with the backward pass. And you look at how information flows on the computation graph. Yeah, I don't know, maybe to further answer your question, if you're saying like, how does information flow from one element of this vector to J, it definitely, even though there's a decoupling between those vectors, there is now going to be a coupling over here. But that coupling is already encapsulated in this sum, which is in this term, and that term we're just reusing. So like if you want to see the full thing, you could just take this and plug that into here in place of that, and now you would see the coupling. But it's sort of hidden because it's encapsulated in there. So yeah, that's the nice thing about this backpropagation approach is you just look at things one step at a time. So when we're doing this, we're sort of skipping over all that complexity by just looking at those two hops. And then we can reuse all the stuff we did before for the first hop, because we've already done that. So it's really just figuring out this next hop, and that one is pretty easy based on this equation. Okay, is that slightly more clear? Okay. So let's see. Okay, so then let's talk about gradient with respect to the parameters. So this again is going to be a vector of parameters. We can look at the kth one. So we're going to use k to index down that vector. And if I ask, if I look at the kth element here and I ask, how does information flow between there and j? So we saw before that information flows through the different i's because that parameter affects all the elements in the batch. So we definitely have this sum over I here. It's multivariate chain rule. Now the question is, if I just focus on a single I, does the kth BO spread to all the different elements in ZO? And to see that, we look at this equation here. We see no. If I look at, for example, the first element in BO, that only affects the first element in ZO, I, right? It does not affect all the others. So across this k dimension, there actually is a decoupling when you go from here to here. So that's why we don't need a double summation over both I and k. We just need a summation over I. Okay, so that hopefully clarifies a little bit about this. Yeah, and then the exact equation for DZOIK, DBOK, that just comes from here. You're looking at fixing I, and then you're looking at fixing a particular index, K in that vector, and you end up just getting 1. Okay. How's that one? Is this one pretty clear? Any questions? Okay, let's talk about the next one. So here we have a whole matrix of parameters, but we're not going to try to do some like direct matrix valued gradient. We're just going to focus on the kth row and lth column here. So kth row, lth column. So how does that information flow? Well, we know that that any single parameter in here affects all the batch elements. So we definitely need a sum over I. Other than that, we might then ask, okay, what about, here again, I'm looking at one element in this matrix, which is going to be the kth row and lth column. So how is that going to affect this? Will that affect many elements in ZO I or just one? Just one, right? Whatever row this is coming from, that is the index of ZI that it will affect. So it's just the K dependence there. There's no need for a summation over K. So there's no summation over K here. Just whatever K we're looking at here, that's the same index within ZO that is affected. And then in order to get this, you can see if you look at this equation and you're looking at the kth element here and you're looking at the lth element here, there's just one scalar number that relates them, which is that W. And so if you take dzok, dwokl, you just get that single AL there. So that's where we get this. Okay, so, and then the other ones are exactly the same. It's just the matrix and vector over here. So for that, we just look, we focus on this. We ask the same questions. The equation has the same exact form. So everything that happens down here is the same as what happens up here. Okay, so that's everything. The only thing left to do now is to write this in a slightly more pretty way where instead of summations, we write things with vectors and matrices. Things get a bit more clean in terms of what they look like, and then for implementation, it would be faster because you could do matrix vector type multiplications and that just generally runs a lot faster in the code because the compiler has an easier time telling the GPU or the CPU, like if you write a matrix multiply, it knows how to organize those computations and do them really quickly. If you write a for loop, the compiler has a much more difficult time understanding how to do all that efficiently. So that's why we like matrix multiplies over for loops. Okay. Everything okay on this page before we move on? Okay, so, all right, so the last thing is really just writing this as vectors and matrices. So here you can see that I'm writing all these things as matrices. So I'm using the same notation that we've used all semester, which is whenever you have a matrix of different training samples, we always have the sample index I going down the rows. So I is going to be going down the rows in all cases, just to be consistent with what we've done all semester. So that means that, K, for example, is what we called this, is the other dimension, or L is the other dimension. Okay, so the first question is, how do we properly write this then in terms of these new matrix quantities? Okay, so this is a column, vector, matrix column. And you can see that the easiest way to write this, if you want to expand this over different I, is you would just stack columns here, right? And you would stack those columns and you'd stack these columns. this here we're stacking across I. Right, that's how we turn one column into many for different i's. We just stack across I. So then we get a matrix, matrix, matrix. And essentially, we're just copying and pasting it, identical thing into the different columns of a matrix here. Okay, so that's what we're going to do. The question is, how do we write that? We have to write it with a transpose because we said that whenever we have this matrix ZH, our convention is to have I come down the rows. And so here, we said I is actually going across the columns. So because I is going across the columns, we've already defined ZH, we just have to transpose it. So I goes that way, K goes this way. Okay, so that's why we have the transpose here. Same thing with X. I must go across the columns here, and the way we always define X is I goes down the rows, so we need the transpose there. Okay, so is this part clear? Okay, so the only thing left to discuss is this. So what we said is essentially we want just to copy and paste this BH. So there's sort of a trick for that. If you have B and then you have a matrix, a row vector of ones, that will essentially, copy BH over and over into the different rows, the same thing repeated. So this is how we extend BH into a matrix, by copying it into every column. Every column of this new matrix would be BH. Is that pretty clear? Okay, so that's basically how we turn this first equation into matrices. This other one is identical. It's just we change the hidden nodes to output nodes. This one, we said that this H function just works element-wise on whatever we give it. So here we're just giving it the full matrix, and it works element-wise on each element in the matrix to give this matrix. So that's pretty easy, and I think the last equation doesn't change at all. We don't really have an easy way of writing this in terms of the matrices because of how we define J. J must work on a sample-by-sample basis, this little j here. Okay, so that's the forward pass. Questions on these matrices? Okay, other than that, the backward pass is really not too bad. We just have to think, how do we want to turn this into matrices and vectors? So here we've written things in terms of the ith element, ith row, kth column. So that's like saying the quantity we had before is the ith row and kth column of this gradient matrix. And if I extract that particular column and row, I just get the thing from the previous page. And so that's pretty easy. What about this? So here we have IL, and K is going to be the variable that we're using for the matrix multiply. So by our conventions, I will come down, because it always comes down the rows of AH, and L must come across the columns. Therefore, on the right side, it must be the same. I comes down the rows. L must go across the columns of W. And now we have the matrix multiply. We have variable K that we're using for that internal multiply. So as we go across here and down there, we're indexing across K. Okay, so this is going to be, so now we can see, yeah. I guess I'm sort of relating that back to this. So you can see WOKL. Yeah, we don't have to have a transpose here or anything because K is going down the rows, L across the columns. So, all right, so is this step pretty clear from here? Any questions on that? Okay. Okay, so this one is actually different. This is not a matrix multiply because if you notice, you just have IL everywhere. So there's no matrix multiplication. This is just an element-wise multiplication. This is a matrix, this is a matrix, but you're just multiplying, you know, like the first thing here times the first thing there, then the second thing here times the second thing there, and so on. So that, we need a special notation for that. That's what this is. This circle dot is the most common notation for that element-wise multiply. It's also called the Hadamard product. Okay, so not a matrix multiply, it's an element-wise multiply. Okay, so then let's look at some of these other quantities here. So here we have the kth element of a gradient as you come down the rows. So that means you're coming down this way with k. And now we have a, okay, this is just a 1. So all we're doing is we're essentially summing this. So we have a matrix where, so if we didn't do any transpose of ZO, I would be coming down this way and K would be going across that way. That is conflicting with this because here K is actually coming across down the columns, sorry, down the rows. So we need to transpose this. And once we transpose it, then K will be coming down the rows just like we want. And then in the other direction, we just want to sum all the elements. So here's the transpose we talked about. And to sum across the columns of this, we just multiply it by a vector of 1s. Right? That just does the sum for us. Okay, so that's how we get this transpose times the 1 vector. So matrix times 1 vector gives vector, just like what we want. The same thing happens here. Okay, what about this one? So over here we have K is coming down the rows, L going across the columns. So here we have the same issue that if we didn't do anything, if we didn't do any transpose, K would be going across this way, I down this way. That doesn't match with this. So we have to transpose this quantity. Once we transpose it, K will be coming down this way, we'll match that. And then I will be the inner sum, which is what we want. And this, we don't have to transpose because I is coming down the rows already. So we just need to transpose this. And other than that, L will be going across the columns to match this. Everything's good. So we just have transpose on the first one. Okay. And then basically the same thing happens for that last equation. Has the same form. Okay, so that's just packing the sums back into matrices and vectors. Okay, so that's it. That's all the hard stuff. We finally have a set of equations. The next slide just summarizes the forward and backward passes altogether. So here's a forward pass written in terms of matrices and vectors. Here's the backward pass, again, written in terms of matrices and vectors. So this is now in a format that if you needed to, you could code this pretty easily in Python. You code it manually if you needed to. Turns out we don't need to because there's these nice software frameworks that end up doing all this stuff for us. We'll talk about that next, but maybe not until Wednesday. So, well, we'll see. We might have a couple minutes. Okay, so that's sort of just the summary. Any questions on backpropagation? Yes.
I have a lot of questions today.
Sure.
The Z, right there at the top where you have
Here?
Z. Why did we transpose to make the I's be the columns when we have the I's as the rows in the chart on the left.
So I wanted to, when constructing these matrices, we have a choice about how we define them, how we construct them. And I wanted to be consistent, where anytime we have a matrix with a bunch of data samples like from a training set or a batch, I want I to go down the rows. So it's always the same, so you don't have to wonder how it's defined. So that's just kind of the conventions for making X. We did this back in Unit 1 already. We said when your feature matrix I, the sample index comes down the rows. So I just said let's use the same convention for the matrix of scores and activations and so on.
So is I going down the rows after the transpose?
No, before.
On the equation?
Yeah, so right. So if because of the transpose, now I goes across the columns, whereas without the transpose, it would go down the rows. So like if you don't transpose it, I comes down the rows. Now if I transpose this quantity, now I is going across the columns.
And we want i's to go across the columns.
Well, it sort of needs to, because the way that we got here was we started with this equation. And this equation says I have column vector here for a specific I, right? And then I have a matrix vector again. And if I want to easily extend this to multiple I can just stack the column vectors left to right. And so if I do that stacking, then I is going across the columns.
Yes.
If we didn't want to do that, we would actually need to reverse this. You could, for example, you could put transpose here, but then you need to move the W to the other side and transpose it. So that's a bit more work. We could have done that. So here's one way to write it. Another equivalent way to write it is to transpose everything. In that case, this goes away, but now this W has to come to the other side and get transposed. So that's just a bigger step from the previous page. So I didn't want to do that. We could have done that. Okay. All right. So, any other questions? Anything here? Okay. Good. So, so this is the summary, and I guess the only thing, if we want to be totally complete, is we've held off on describing some of these cost derivatives. Although I think we've sort of seen them before, but here's a couple examples. Like if you have binary cross entropy loss. Back in Unit 5, we essentially said it's the sum over the batch in this case, or the training set, however you want to build all your different data samples, sum of the element-wise cost, which has this form. So we derived this back in Unit 5, and so now the only thing to figure out is if you want to do J prime, like dj dzo, that's pretty easy, right? It's just differentiate the log. So by the chain rule, you get this. And then differentiate this, you get yi. So this is what you would use in the very first step over here. On the other hand, if you're doing k-area cross entropy, then we have this softmax thing we derive for multinomial logistic regression. And if you want to take the derivative of this with respect to ZOIK, then you get this expression. And so that's what you would use over here. So it really just depends on, are you doing binary classification, or are you doing k-area classification? You have more than two labels. Okay, so so that's pretty much all the hard stuff with back propagation. Really what we're going to do next is just talk about how we actually implement this. So we're going to go through a whole bunch of code to understand the particular way in which the framework we are using, which is called PyTorch, how does that handle it? Just sort of as a brief introduction, there's a whole bunch of different ways you can code deep learning models out there. Most of them are written in Python, not all of them. You can do it in MATLAB. MATLAB has some stuff too, but it's sort of a standalone thing. It's not that well developed. So everyone who does this seriously works with Python. And then in Python, the main frameworks that we have are TensorFlow, PyTorch, Keras, and I would say probably the fourth one nowadays would be JAX. Some of these other ones are sort of proprietary to different companies that maybe if you go to work at Amazon, you might be using something in particular, but most other places use one of these other 4 things. And we are going to use PyTorch because in some sense it's the cleanest. So TensorFlow is the original one. It's really mature for deployment, but the trouble is that it's just kind of difficult to use. There's a version 2 from a couple years ago. They've simplified it, but it's still difficult to use. My PhD students, they've tried both, and they say, yeah, just PyTorch is much better. Keras is sort of an interesting thing. It's really sort of a layer of coding that runs on top of some of these other frameworks. And it makes everything super simple. So you could like code a neural network in one line if it's a very particular kind of network that's very common. But the trouble is it's overly simplified. If you really want to do anything custom or if anything breaks, it's hard to figure out what's going on because it's just, you don't have much control or much visibility into what's actually happening. So it sort of oversimplifies everything. PyTorch is a nice happy medium. It's easier than TensorFlow. It makes the most sense. It's what most people in research and academics are using these days. And if you want to read some articles that compare these things, there's some links here. But we are going to focus on PyTorch, and we're going to go through the way that PyTorch does things, which is a very particular recipe. And we'll go through all the steps. There's a whole bunch of details, but we'll just go through step by step next time. So, see you guys on Wednesday.